Welcome to Chapter 9, Deep Time, How Old is Old. You can also refer to this chapter as Geologic Time, and in it we will discuss how scientists understand how we record the history of Earth. We're skipping chapters 7 and 8 because in this abbreviated semester we only have time to focus on certain topics. And Chapter 7, which is about mountain building and geologic structures, and Chapter 8, which is about earthquakes, are not as relevant to Floridians as are other chapters in this textbook, because we do not have any mountains in Florida, nor do we have significant earthquakes because we're not close to a plate tectonic boundary. If you're curious in learning about these topics, I encourage you to read the textbook about them on your own. So now we'll go into geologic time. There are two ways to think about geologic time. These are in terms of relative ages and numerical or absolute ages. The first part of our lecture today will discuss relative ages, which is defined as how old geologic materials are in relation to one another. So in the diagram to the right, we have the units that are on the bottom being considered as older than the units on the top, which are younger. This is an example of relative dating. If you were to say, my brother or sister is older than me, that is an example of using relative age differences. The second topic is numerical ages, which is actual ages in years of any geological material. So on the diagram you see differences between 545 MYA, which stands for million years ago, all the way up to 495 MYA. So you see that these are actually numerical or absolute differences in age that can be quantified. In between discussing relative and numerical ages, we will discuss fossils and the fossil record. One concept that's fundamental to understanding relative dating is the concept of uniformitarianism, which is defined as the physical processes operating in the modern world also operated in the past. One example of uniformitarianism is these mud cracks in the photos below that show modern mud cracks are forming and look the exact same way as they formed and look in ancient rocks as old as 300 million years and older. Uniformitarianism concepts are very important in understanding sedimentary geology and principles of superposition and cross-cutting relationships, which we'll talk about momentarily. So these principles used to determine relative ages include original horizontality, superposition, cross-cutting relationships, baked contacts, and inclusions, and we'll go through each one separately. The principle of original horizontality tells us that layers of sediment, when they're first deposited, are roughly horizontal. This is a result of gravity producing sediments in horizontal sheets, which is in the photo on the left. Then we translate that information to rocks after they've been lithified from sediments, and we understand that horizontal beds in these sedimentary rocks can then also be assumed to be in their original orientation. This is shown in the photo on the right. The principle of superposition indicates that if rock layers are laid down horizontally, undisturbed beds have been laid down in sequence with the oldest beds laid down first and at the bottom, with each layer of sediment or sedimentary rock on top of it must be younger than the one below it. So in the figure on the left, you have an example of pouring some sand or sediment into a glass beaker, and we understand that if we do this, then the oldest sediment, or the first sediment poured, is on the bottom, whereas the most recent sediment poured is on the top, which would be the youngest. And here's an example in an actual rock outcrop on the right. Cross-cutting relations refers to the idea that if one geologic feature cuts across one another, that the feature that has been cut must be older than the one that is doing the cutting. So in this example, we've got an igneous dike intruding into some rock layers that are laid down horizontally, and it cuts across these different layers and the context between them. Thus, the dike must be younger than the 3 sedimentary layers on the bottom of the figure. However, the top reddish-brown layer was not cross-cut by the dike, so this layer actually must be younger than the dike. This is cross-cutting relations. Then we have baked contacts. So this principle states that if an igneous intrusion bakes or cooks the wall rock that it intrudes, the rock that has been baked must be older than the intrusion. It's very similar to cross-cutting relationships. Then finally we have the principle of inclusions, and this states that a rock containing an inclusion or a fragment or fragments of another rock must be younger than those inclusions themselves. So in the example below, we have pebbles of basalt in a conglomerate on the left that must be older than the conglomerate. On the right, the fragments of sandstone in a basalt sill must be older than the basalt containing them. So these are 2 examples of the principle of inclusions. So we use these 5 principles based on the concept of uniformitarianism to unravel the order of past geologic events. One common thought problem for introductory to geology students is to take a cross-section of geologic materials and determine the order or sequence of events that have occurred using these principles of superposition, cross-cutting relationships, etc. So in the figure below, we have sedimentary units that have been deposited. There are igneous units and faults that are cutting across them and baking them. And if we do the problem correctly, we establish that at time 0, at the first event was possibly the deposition of one unit, and then we go all the way to the deposition, erosion, or intrusion of the final unit.